Hey everybody, it's Dr. Green here with integer linear programming number 3. So today we're going to talk about something a little more complex than our previous problems. The example is Remington Manufacturing. They're planning on their next production cycle and they can produce 3 products. Each product requires machining, grinding, and assembly. There is a per unit profit that's been estimated. There's also a setup fee if they want to produce that product. Now this is what we call a fixed charge problem. So if I decide to manufacture a project, I incur a fixed charge. So we want to figure out how to maximize profit while meeting our constraints. So I think the initial variables here are very clear. We are deciding the number to make of each of product 1, 2, and 3. So go ahead and give those a nice red border to indicate that that is a decision that we're making. Okay. We have all this stuff going on here, so let's take our amount available. This is real classic stuff at this time, so you should be able to do this in your sleep. We'll take the sum product of our decision variables along with the hours required for each. We know that those must be less than or equal to my amount available. So I have my amount used, my amount available. I'm just going to bring those down right here. We also have unit profit, right, which is the sum product of the number made along with my unit profit. Okay. So here is where we start to run into trouble. This is where the problem gets a little tricky and things change, is this decision, do I or don't I make each one of these products? So I think it's very obvious if you're saying this is a yes-no question, well, that's a binary decision, a 0 or 1. So based on what we've been doing in this section, I'm going to go ahead and move these down here a little bit. We need to decide, should I make any of these products? Not only are we deciding the number to make, but should I make these? Now these are going to be decision variables as well. They're going to have a red border, and they are going to be binary variables. So this is going to be integer, this is going to be binary. Okay? So in order for this problem to actually work appropriately, what we have to do is we have to find a way to take these 3 variables, x1, x2, and x3, and link them with these 3 binary variables, y1, y2, and y3. So the question becomes, how do we do that? Well, the way that we really do it is we come down here, we say, should I make? And what we want to do is we want to generate a linking constraint. A linking constraint comes of the form x1 less than or equal to m1, y1. Right? Now you might be saying, well, what's m1, y1? m1 is simply a large value that we refer to as m that gives us a bounds. Okay? So what we're going to do is number to make. We're going to set an upper limit saying this must be less than, the number I produce must be less than or equal to my upper limit. Well, what is my upper limit? I have 2 ways of doing this. One, I can set an m value. Okay, so let's just pick a big value. We don't have to actually worry what this is. It just has to be anything, to be honest with you. And we can say this, my upper limit, is my binary variable multiplied with this large m value. And it is the same all the way across here. Now you see that's complaining because I have y's in here. Okay, so we can actually do this very cleanly right here. Okay. There is another way we can do it that is a bit more mathematically robust. And we'll put our m value right here in between these. The other thing we can do, well, we have all these constraints down here, right, in resources. So if I want to pick the actual maximum value made, what I can do is, well, say, what if I made only product 1? Well, if I made only product 1, the biggest number I could make would be the maximum value of machining hours divided by machining required, grinding hours divided by grinding hours required for product 1, or assembly hours available divided by assembly hours required for product 1. Okay, so I can actually lock those three values there because they're going to stay the same. And you'll see in this case what it ends up giving me. Oh, that's not going to work out so well, is it there? We want to make this down here, so we want to look at product 2. Oh, you know what? I did this whole formula backwards for y'all. This is actually the maximum value of machining hours available divided by machining required. Not comma, divided by. And the maximum of grinding hours required divided by grinding hours for product 1. And the amount of assembly hours required divided by assembly hours required for product 1. Okay, so the max is still 300 there. We can actually drag this right across, and you'll see all we're doing is dividing the maximum amount of my resources available by the required resources. So you'll see this actually gives me 3 different M values, and then at that point what I can say is, oh, you know what, not C6 times this, but C6 times this gives me my upper limit. Now there are some computational advantages to doing things this way. It gives us much tighter bounds, which is a very nice thing to have. Which may actually help us solve our problem more quickly. So now that we've generated our nice linking constraint using our M value, either a very large value or a calculated value based on the resources available versus those required for an individual product, we can also look at our setup costs, which are also very easy, right? We have setup fees. Those are fixed costs, and we only incur those if I have a 0 or 1 value. So then I have my total profit here, which is simply my profit minus my costs. These should all be dollars. We'll give this our beautiful double border. And we have our problem formulated. How do I solve it? Data, solver. Okay. I want to maximize my profit by changing 2 sets of cells. And remember, just hold down the command key and you can add that second one in. Subject to the constraints that my cells are less than or equal to my upper limit. My number of makes less than or equal to my upper limit. My amount used is less than or equal to my amount available. These, since I can only make integer values of products or integer, and these are binary. We are going to use simplex, and we are going to say solve. Let's see what happens here. Solver found a solution. Okay, we're making 0 of anything. So what does that tell me? I want to maximize my profit such that this, but none of my constraints are met. Nothing has happened here. Let's try this one more time just to make sure there wasn't an error while it was trying to solve. Solver found a solution. Okay, so this is a very interesting problem. Let's go ahead and clear out our cells and make sure everything is calculating correctly. So if I make 1 of product 1, I get my 265. If I get that, that's right. My linking constraints all appear to be correct. Okay, I have my unit profit. Let's try this one more time. Maximize C18 by changing C2 to E2, C6 to E6. I have these. Well, let's just take care of these and see if we can get it to solve a relaxed version of our problem appropriately. Okay, so we can't get it to solve. So at this point, I have to tell you that the built-in solver for Microsoft Excel does not always work that perfectly. Sometimes it hits limits, it has some problems, it is not perfect. When that happens to me and I'm using Excel, well, the option is to go to another tool. That other tool, we'll close this, is OpenSolver. You'll see you can install this. It's opensolver.org. You can click the latest stable version or click download and install. When you do this, it'll take you to the download page. You will go ahead, you can download it. They've released a beta version, all this kind of things. So you can download this, available downloads, right? linear zip file, OpenSolver for Windows, also available for Mac, all this kind of stuff. You'll get a file. I actually downloaded it just for Windows anyways. And if we go to our downloads folder, you'll see it's right there. I've opened it up. There is an XLAM right there. Double click on that. It will open an Excel. Tell it to enable macros. And then you will see this magic new piece to your toolbar. Model, solve, show hide model, quick solve, OpenSolver with all these options. If you click on model, you get to fill out your model. Now this is very, very similar to the solver you're used to. You pick an objective cell, we already have that. Variable cells, we have those. We have our constraints. You'll see these are over here. They don't have these nifty pop-ups, but they're right there. You can delete this. Make unconstrained variable cells non-negative is what that says. Show named ranges, all this kind of stuff. From here, we can just save our model. And you'll see it'll actually mark this. We can show and hide the model. It'll show us everything that's going on. It highlights our decision cells very well, our objective and our constraints. And when we're ready, we can click solve. And you'll see this will work. There we go. It has solved our formulation. Now here is a correct solution. You'll see we are making product 1 and 2. Oh, now see, I did that. The thing you do here is show hide model. That goes away. You have a nice solved model. Our constraints are met. These constraints are met. Our decisions are made, and our model is optimized. So now, not only do you know how to do fixed charge problems, but you know how to use a tool in addition to the built-in solver in Excel. You know how to use OpenSolver. OpenSolver you can dig into. It does have many, many more features to it. It has many more powerful solvers available to it. It works with Google Sheets. It does a whole lot of stuff. You'll see it actually uses other solving engines. It's a very, very powerful tool. You can check out the blog, look at their to-do, all these things, but it is a strong and very good tool. So with that, you should be good to go.